Welcome. In this video I'm going to show you how you can determine various measures of qualitative variation using Microsoft Excel. I'll have a separate video where I'll be using my stikpet E add-in, which makes it a lot easier. But if you don't want to use that, then this is the video for you. These are all the measures that I'm going to go over, so this video is going to take quite a while. I tried to group them, as you can see, but don't pin me on this grouping. Most of these are fairly straightforward if you go over the formula. I won't go into details on which one of these you should use or how to interpret them too much. It's just about how to obtain these values. So let's dive in. It's going to be a long video, so sorry for that. First of all, there's the Freeman variation ratio, which is basically the percentage of cells that do not fit into the model category. Now, for most of these we will need the frequencies, and you can actually obtain them by simply using a COUNTIF function. Once that's done, you can actually simply find the maximum frequency, how often that maximum frequency actually occurs, and then the Freeman the variation ratio is simply 1 minus this one multiplied with that one divided by the total sum. So that's what this one is doing. The Berger-Parker Index is actually the same, but then without the 1 minus. So this is the percentage of cells that or cases that do fit into the model category. So it's the same. We do the maximum again. We'll do again a COUNTIF, and then simply do 1 times the other divided by the sum of all the frequencies. Then there's the model variation ratio, modified variation ratio from Wilcox. Again, we find the maximum, then we subtract each frequency from the mode and sum the result. So here we subtract from the mode the frequency of each category. Of course, the first one is 0 because that is the mode, and then we sum them all up. We determine the number of categories, which in this case is 5, and then we divide that sum over the total times the number of categories minus 1. And that's the Wilcoxon modified variation ratio. Wilcox also did a range, so again the maximum. Then we also need the minimum, so the minimum of these. And forgot to make that one nicely in the blue color. And then it's simply the difference between these two divided over the model, and then subtract subtract this from 1. Alright, then we have average deviation. That kind of looks at averages of the frequencies, so basically average of those. It then subtracts from each of them that average and takes the absolute value. And then we sum all of those results and the number of categories again. And then this scary looking formula, but we have everything we need. That sum, that weird looking E, is just this value, the number of categories we have, and n is the sample size, which is over there. So we can simply fill out the formula and get our result. Then we get to the VARNC, which is also known as Gibbs-Poston M2 or the Smith-Wilson E1. We again start with calculating the average, but now we subtract this average from each and square the result. So rather than taking the absolute values, sum all of this again, and then very similar as the previous one, but now there are some squares in there, and you get your Wilcox and VARNC. That's like the variance for quantitative measures. There's also the standard deviation, which in essence is taking the square root. So again, we start calculating the average. We do exactly the same as with the previous one, determine the number of categories, and then just fill out the formula in the same way with all the values we've obtained, and we get our result. Then there's Gibbs-Poston M4, which also uses the average and also again the absolute values, but it divides it by something slightly different. It doesn't take into account how many categories there are, so there's no K involved. And we get that that's 0.69572. M5 is similar again, does the exact same thing. We have the absolute differences, but now it does take into consideration also the number of categories, as you can see, and we have ourselves 0.62. M6 is again also very similar, but does it in a slightly different way. Again, the average, the number of categories, and then finally just the formula. Then we have entropy measures, the Shannon entropy or Shannon-Weaver entropy. That uses a logarithm scale, so from the proportion. So we simply first divide each frequency by the total, and then take the natural logarithm out of that using the ln function. And then the Shannon-Weaver entropy is minus the sum of those multiplied with those. So these multiplied with these, and you can use sum product to do that in one go, and then just put a negative in front of that. Alright, that brings me to the Wilcoxon HREL and or Pielou J. Same thing as with the Shannon entropy, but now it's using the log base 2. And then we divide by log base 2, so it should give the similar result. But now also k is involved here, so we get again the sum product with a negative in front of it. Then there's the Sheldon Index, similar as with the Shannon entropy. Again, the sum, you even calculate that one, but you now adjust it for the number of categories. So you divide it, you raise it to the power e to the power of that Shannon-Weaver entropy, and then you divide it by the number of categories. Then there is Renyi Entropy. I hope I'm pronouncing this correct. It requires an alpha value, so you set that one first, and then you raise the proportion to that alpha level. You can then use the log 2 from each of those of the sum, and that should give you then the Renyi Entropy. There's the Heip Index, which again uses, similar as the Shannon, the natural logarithm. Again, it even uses the Shannon-Weaver entropy, as you can see, so that's all the same. And also this one adjusts it for number of categories, but in a different way than the previous one. It takes the Euler number to that power of that Shannon entropy minus 1 and divide it over the number of categories minus 1. Alright, then we get the Hill diversity one. We're getting closer and closer. Still a few to go. Similar as the previous one again, of course, but you take, in this case, simply the sum of all of them if alpha is not set to 1. And then you raise that to the power of 1 over 1 minus that alpha level. If alpha equals 1, you simply use the previous one. The Hill Eveness is actually using the Hill diversity. So the formula, you can just see it over here. The basic start is the same, but now you have an alpha and a beta, so basically you have 2. For each you calculate the Hill diversity measure, just as before, and then the Hill Evenness is simply dividing those two by each other. And I forgot to make this on nicely in blue as well. Then Bulla E, we take the minimum of the proportion or the expected proportion, which is 1 over k. And then we have this scary looking formula, but actually if you look closely, O is simply the sum of all of these, and everything else we have the k and the n. So it's just being a little bit careful with your parentheses, but then it should work out, and this turns out to be 0.62. Bulla D is very similar, as you can notice. It's hard to even find the difference, but the difference has to deal with that this one is an evenness measure and this is a dominance or diversity measure, and it simply takes the E and then you multiply it by the number of categories. Then we have Smith-Wilson E2. We take the proportions again, we square these, and then we sum all of those. Once that's done, we can actually simply take the natural logarithm with a negative in front of it of that sum and divide it over the natural logarithm of the number of categories. E3 is very similar. We square the results again, so we do the whole same calculations, but now we actually divide it by 1 over the previous one times k. So the sum times k. Then we get the Wilcox MNDIF. As you might notice, this takes a little bit more effort because this is actually also all some formulas, and that's a big looking formula, because what this formula over here is actually implying is to take all possible combinations and differences from each frequency. So here is the difference between this one and that one, this one and that one, and we have to do that for all of them. We of course only do that once, so that's why this formula looks so big. Then we have the number of categories, which was 5, and then finally we can calculate 1 minus the sum of all of these over n times k minus 1. Alright, then we have the Gibbs-Poston M1, again squaring the proportions, and then simply doing 1 minus the sum of all of those squared proportions. Then we have Gibbs-Poston M3, again squaring the proportions, and then in this case slightly scarier looking, we need the minimum proportion, so we can simply do min, and then we have everything we need to fill out this formula. It's 1 minus the sum of those squareds, minus then again the p min, which was over here, here, and then we do 1 minus 1 over k minus p min. Then we have Simpson D, again squaring the proportions, but also having the frequency times the frequency minus 1. So that's slightly different. We do that for having here the numerator, which is then simply the sum of those divided by the sample size times the sample size minus 1. For the population version, he's using the squared values, so we can then simply take that value, and that's then the Simpson D for the population version. Often the complement is used, so we do a 1 minus each, so that might give you a different variation sometimes. Last but not least is the Kaiser B, and that's finally then the last one. It takes the proportions but multiplies it with the number of categories, and squares those results. Now, so actually this is pi times k, and this should not be in subscript, so let's undo that. Okay, alright, so, and then this scary looking formula, this big pi is actually the product function, so it's similar as sum, but it multiplies every time. And as you can see, what it does is we do that for each of these. We square those results and then divide them by n. So that takes care of this part. There's a 1 minus in front of it, so that's that one. And then it says to actually raise all of that to, or before we do that, we have to take the square root, the kth root out of that, which is the same, but then squared, so that's the same as 2 divided by that k. And then we take the regular square root out of this and then do a 1 minus. And that's more than 25 different measures of qualitative variation with Excel. Sorry for the long video, but hopefully it was helpful, and thank you for watching.